Okay, let's use our kinematic equations to solve some basic kinematics problems. Let's start with a car is traveling at 33 meters per second and it needs to stop to avoid hitting a deer. It slams on the brakes and skids to a stop. Later, when the deer wants compensation, an accident reconstructionist measures the skid marks to be 70 meters long. What is the acceleration of the car? Actually, let's make that part A. What is the acceleration of the car? And part B, how long did it take the car to come to rest? Okay, so this is a one-dimensional kinematics problem. The car is moving a straight line, and we can apply, and we can assume it's accelerating constantly, unless it's obvious or otherwise stated. We can assume the acceleration is constant, so we can use our kinematic equations in order to try to solve the problem. So where do we start? Where we start is we always start with drawing a picture. So let's draw a picture. The car is going at some initial velocity. It ends up. Now, where does the car end up? Well, it ends up 70 meters down the road. Don't worry where the deer is. The deer's sitting on top of the car. It ends up 70 meters down the road, but what else do we know about that? We know we want to find the time and the acceleration, so we don't know time. We don't know acceleration, so we should write all this down. Ooh, we do know V0, because remember there are 5 variables, and we got to figure out how many we know and how many we don't know. V0 is 33 meters per second. V final, we don't know. And delta x. Oh, delta x we know. It's 70 meters. Aha, but I just made a mistake. Or I tricked you, one or the other. What is T and A are what we're looking for, right? We're looking for time and acceleration. But what about V? What is V? V is the final velocity. What's the final velocity? Well, the implication here is the car has come to a stop, so we do know the final velocity. The final velocity is 0 in this case. Careful, because in our constant acceleration problems, the final velocity is not always 0 where you think it's going to be. But in this case, it definitely is 0. So we have 2 unknowns, and we've got 2 unique equations. We've got 3 equations we can choose from, but we are only going to be able to use 2 of them to solve the problem. Okay, so let's let's continue. We haven't finished setting up the problem yet. So in setting up the problem, the one other thing which we haven't paid attention to, which we've got to be very, very, very careful about, especially when we get to slightly more complicated problems, is which direction is the positive direction. Now, everything's moving in the same direction here, so we can keep everything positive. But we have always got to really think about which direction is the positive direction. So I'm going to call the direction of motion, and that will become important here in a second. We're going to call the direction of motion positive x. So that means my initial velocity, what's the sign in front of my initial velocity? Because I just gave you a number, 33 meters per second, but it's got a direction as well. These are vector quantities. So the sign is plus. It's going in the plus direction. What's the sign in front of my displacement? It's displacing. So look, you got to look at the arrows. This is what I'm telling you now seems very easy, but this is what we have to do when we get to more complicated problems. And I'm even looking at my camera and pointing my finger, even though you can't see me. Okay, so this arrow, V0, points in the same direction as this arrow, plus x. So that's why there's a positive sign in front of V0. Whoops. This arrow, the 70 meters, points again in the same direction as the plus x. So that tells me that they're pointing in the same direction, they're the same sign. That's why I drew these arrows, so that I can determine whether it's positive or negative. And you have to define your positive direction. In this case, again, I just said, oh, let's just call the direction of travel the positive direction. I could have called the direction opposite travel the positive direction. It doesn't matter. But in this case, I called that direction positive direction, which is why I've got plus signs in front of V0 and delta x. Every step I've done here, drawing the picture, writing down the 5 variables, and choosing my directions and putting in the explicit signs is essential for solving these problems. Now what we do is we look at the relationships and choose the correct relationships in order to solve what we're looking for. The first question is, what is the acceleration of the car? So we can look at the equation and say, ooh, all three equations have the acceleration of the car. Hopefully I can just use one. I might have to use two. Well, I know v0, v, and delta x. So I can look at the first equation, right? Look at the first equation and say, okay, I know delta x. I don't know t. I know v0, and I don't know a. That's two unknowns. Hard to solve. One equation and two unknowns. I can look at the second equation. I know v. I know v0. I don't know a, and I don't know t. Ooh, two unknowns. Well, I could take those two equations, solve them together. Two equations, two unknowns, to get the answer. But let's look at the third equation. Third equation. I know v. I know v0. I don't know a, and I do know delta x. So it's one equation and one unknown. So the easiest equation to use to solve this problem is going to be equation 3. So to answer part A, I can take equation 3, v squared equals v0 squared plus 2a delta x, and go ahead and plug in my numbers. Right? V final is 0. 0 squared equals v0, our initial velocity, plus 33 meters per second squared, plus 2a is our unknown, delta x is plus 70 meters. And a couple things to notice. I'm doing everything very carefully here that you will need to do in every problem you solve. You shouldn't skip the steps. A couple things to notice is that I carry my positive signs to make sure I'm paying attention to direction. I carry my units to make sure the units work out. Right? And I think that's it. But the units and the signs are really important. So now I'm going to go ahead and solve for my unknown. A is equal to, now we've got minus 33 squared, I'm doing the algebra, divided by, I left off my units. So I carefully solve the algebra to get this, and what I end up getting, you can't drop your minus signs, you got to pay attention to those, and what I end up getting, where'd that minus sign come from? Pay attention to where that came from. I'm not going to tell you, you should figure it out, it's algebra. And so what I end up getting, and I'm going to also make sure that the units work, because in the parentheses I've got meters per second quantity squared, or meter squared over second squared, and we've got a meter on the bottom, so 1 meter will cancel and 1 meter will be left, and so what I end up having is, and I plug that into my calculator and I get minus 15.6 meters per second squared. So the sign comes out to be negative, the units come out to be meters per second squared, and the first question you should ask is, are the units correct for the quantity I'm trying to solve? I'm trying to solve for acceleration, and the units for acceleration are meters per second squared, so the units worked out right, so that means I probably plugged in right. And the minus sign, what does that mean? The minus sign means that the acceleration is in the negative x direction, right? Now look at the picture. Which direction is the negative x direction? The acceleration is in that direction. Does that make sense? Yes, it does, because the car is slowing down in the plus x direction, which is the same as speeding up in the minus x direction. So it's the same as the acceleration pointing in the minus x direction. So that is correct. And actually, we could have put that in the picture to begin with. We could have said, oh, I know the acceleration is in the minus x direction, so let's make sure it turns out to be negative. So this is the answer, 15.6 meters per second squared. I'm actually not sure that's a reasonable acceleration for a car. It seems a little high, but I just made up these numbers, so we'll just go with it and just say it's a really good car at stopping. I think that cars going, 33 meters per second, which is like 60 miles an hour, take more like 200 meters to stop instead of 100 meter. Okay, so that should make some sense. You should think that through. But what about part B? How long did it take the car to stop? Okay, I'm going to have to go to the other page, but let's just first of all look. We can go through the same process. How long did it take the other car to stop? We now know A is minus 15.6 meters per second squared. And we can go ahead and look at how long is time, so we can only use the first or the second equation. And to me, it looks like we could absolutely use either one, But the second equation is going to be the easier one. And actually, maybe I can just write it on the same page. You shouldn't squish your stuff together like this, but I'm going to go part B, right? We're just going to say, oh, if I use V equals V0 plus AT, that has, we know the velocity. The final velocity is 0. The initial velocity is plus 33 meters per second. I didn't leave myself enough room. Okay, so that's what I end up getting, is when I plug in what I know and what I don't know into the second equation. We could have used the first equation. Either one works. Both of them have time in it. And so then I can solve for t. T is equal to minus 33 meters per second. I'm going to subtract that from both sides, divided by minus 15.6 meters per second squared. I did 2 algebraic steps at once, just like I did in part A. You need to repeat this algebra for yourself to make sure you know how to do it. And what do we end up getting? We end up getting about 2 seconds. What I get is positive 2.12 seconds. The minus signs cancel, so I get positive 2.12 seconds. First question we should ask is, do the units make sense? Yes, we were looking for a time. Second question is, does the sign make sense? Yes, we started the problem at t equals 0, so it should be a positive time, not a negative time. It is possible to have negative times in problems, but in this case it should be a positive time. Does the time make sense? Is it a reasonable time? Is it not 10 years? Is it, seconds? Yes, it's 2.12 seconds. So that seems like a reasonable answer, and that is the answer to part B. Done, check, next.